Yes. My presentation concerning explainable cloud forensics for virtual machines in heterogeneous distributed centers. These are the contents of the presentation. Introduction and background. Cloud computing, delivery of computing services and resources over the internet in terms of software platform and infrastructure. These visualizations here, below here shows the cloud data center growth, the cloud market share, and the cloud security incidents. The cloud market share is dominated by AWS. Cloud computing, it is built on a virtualization technology that involves the creation of various instances of software, hardware, be deployed on the internet, on the cloud for user access. So this diagram here shows the server computer or the host computer being virtualized to hosting 5 virtual machines which are hosted in the cloud for public access. Virtual machines, these are just virtualized emulation of a physical computer system, a software-defined computer system that is created by a hypervisor software application. Now this diagram shows the infrastructure or the architecture that makes up a cloud computing environment. It consists of layers, the physical layer, the virtualization layer, and then the service layers. A data center, it is a facility that's dedicated to provide enormous storage of large volumes of data. It is built on components of computer, server, and storage. Now, it is through data centers that cloud service providers are able to provide cloud computing services to the end users. Heterogeneity of the cloud of the data centers means the provision of a wide range of computing resources in order to dedicate to meet various user needs. And the resources or services are being provisioned to your users that are geographically distributed. Cloud forensics. Cloud forensics it is a term that involves the identification, examination, collection, analysis, and reporting of incidents that are happening in the cloud computing environment. Now, traditional cloud forensics analysts use what we call, cloud forensics analysts use what we call traditional cloud forensics methods. For example, FTK, which suffers the problem of penetrating the virtualized layers of abstraction, the one we saw, the layers of abstraction that makes up the cloud computing environment. They cannot analyze massive volumes of data. They lack forensics explainers. They have high false positives, and they cannot adapt the heterogeneity of the distributed nature of the cloud environment. They are also slow due to the fact that to extract forensics evidence from a hard disk having 2 terabytes, the cloud forensics analyst may take 85 hours to extract forensics evidence. Problem statement. So, problem statement, here we have seen how cloud forensics, traditional forensics methods suffer the problem of penetrating the virtualized layers of abstraction to extract forensics evidence. Then they have high false positives and false negatives. They cannot adapt to the heterogeneity of the cloud environment that consists of multiple cloud data centers that are geographically distributed in various locations. So retrieving evidence using traditional methods in such an environment, having cloud data centers geographically distributed with their heterogeneity and with their virtualized environment makes extraction of forensics evidence and forensic evidence from the environment difficult and complex. And also the volumes of data that are generated from the cloud, it is too much. So making analyzing That too much data makes the whole process complex when the application of traditional forensics methods when traditional forensics methods are applied. Main objective to develop a framework that penetrates the abstract layers of abstraction to detect, analyze, examine crime-related incidents and classify VM instances using the data generated from the VM log information from the VMs spread across various geographical locations. The hope of explainable artificial intelligence. Specific objectives: detect and identify the status of the VM instances, identify important features needed by forensic analysts for evidence detection, build, train, and evaluate deep learning models, implement explainable artificial intelligence. Research contributions. So this framework could be used by cloud forensic analysts to classify VM instances deployed on the heterogeneous cloud environment to ascertain whether a certain VM is under attack or normal. Then cloud forensics investigators will be in position to identify important features responsible for branding virtual machine under attack or normal and coming up with various mitigation measures and also finding out the root cause of such attacks. Then detailed forensics reports can be generated from the explanations that are being projected or portrayed by the explainable AI tools. Related works. This table here shows some related literature, dataset description, and methodology. This is the proposed framework. I used what we call the KVM dataset, inputting the features. I did data processing analysis. I did feature engineering, model training. Then I did model testing and evaluation, model explainability. I did model selection and model deployment. From this graph here, we see that most of the virtual machine instances are normal. Then few of them, around 24% of them, are under attack. Model building, training, and evaluation. Deep learning models were built, and this is the evaluation table shows the evaluation model evaluation on the test set, and we see that feed for neural network, ANN, CN, and CNN are the best performing models. Application of explainable AI. So I implemented line sharp and feature permutation importance. Now this slide shows the application of explainability on AI artificial intelligence on a feed-forward neural network. This is for the first VM instance, this line plot. This is for the tennis. This is for the 1345 VM instance. And you will see that memory last update, it is the feature here that the model relies on to make its prediction. Application of sharp explainable AI on the feed-forward neural network. Here we see still memory update. It is the first three features from this line, from this waterfall plots, they are consistent. So this blue waterfall plot shows that the virtual machine instance is normal. Then the red waterfall plot shows that the virtual machine is under attack. I implemented feature importance explainable AI, feature permutation importance explainable artificial intelligence using the feed-forward neural network, and still memory last update is one of the most dominant feature for the model, which the model relies on to make its prediction. The feature permutation importance works in such a way that it shuffles the dataset. Then after shuffling the dataset, it compares the baseline performance with the performance on the shuffled dataset. And we see that once we shuffle the dataset here, the performance goes down, demonstrating how much the features are in helping the model make its predictions. Model selection and deployment. So I saved the model plus its scalar, pushed them to the version control system plus other dependencies, then generated a Docker image, the Docker Hub, a standard platform for storing Dockerized or containerized images. Then after that, I deployed on Render. Render provides a runtime environment for the deployed model so that they can be accessed for the user to send the data of the model and return predictions from the model from using a web form. Then I did model performance monitoring. For example, previously, the model was returning only normal VMs, even when I apply various elementary data. But I went to the version control system. I accessed the app.py file. I made some adjustment in the app.py file scripts, a Python script. Then I committed the changes, pushed to Docker Hub, and then I was in position to access the attack virtual machine instances. So in case something is not working well, we can use the model performance monitoring phase by doing what is termed as continuous integration and deployment, and then push to the version control system, push to Docker Hub, and then access the model output. So this is an iterative process that keeps on running. These are screenshots after accessing the deployed model via a URL. So as we can see, time spent by the virtual central processing unit to execute the guest code here, it is 456 micro nanoseconds. So here, the virtual machine here has a CPU which takes a much longer time, 115 billion nanoseconds. So this is a normal VM, so it takes in this this one corresponds to a normal VM because the spikes, they are no escalated, or it has less computational load. Here, this virtual machine here has too much computational load that makes its processor take longer time to execute its instruction, which makes this virtual machine to be slow or compromised, rendering its services inaccessible when it is deployed over the internet. A signature of a disputed denial of service attack. Conclusions. Here we see how Lime and Sharp can be used to help cloud forensics analysts to come up with valuable evidence to be presented. And also, we see how explainable artificial intelligence can be used to map attack signatures with known threats which are happening in real life. For example, that brute force attacks data because brute force attacks or disciplinary service attack, what they do is that they increase on resource utilization of the computer system in terms of CPU, memory, and maybe disk usage. So one of the limitations which I got is that the SAP consumed too much computational resources. It is computationally intensive, and therefore causing my system to slow down, rendering me to keep on restarting my computer for quite several times. Then, more hypervisors should be used apart from KVM, and VMs should be, or datasets should be created using other cloud management platforms like Microsoft Azure Arc or OpenStack, using different KVM, using different hypervisors. For example, we can data can be used using QEMU, Quick Emulator or VirtualBox. Then the data sets need to be more annotated data need to be constructed so that maps a particular VM with its corresponding attacker type instead of relying so much on the attack signatures, vectors, and patterns. So that cloud forensic analysts can be in position to able to understand that this particular VM was maybe compromised by a distributed denial of service attack. Because attack signatures can be misinterpreted by cloud forensics investigators. The references. Yes. Thank you, Doctor. That's the end of my presentation.